We can compare the electrical current to the current of water that flows in a river or a creek. Like the water in the creek moves from the higher ground to the lower ground, or from a higher to a lower potential energy level, so the charges in an appropriate medium do. We call the appropriate medium a conductor to highlight the fact that it allows charges to freely move inside of it. Now, charges can be positive or negative. In a copper wire, for example, all the copper atoms are disposed in a three-dimensional grid and cannot move unless you melt the wire, of course. However, the electrons in the most external orbital have the capability of moving very easily from one atom to another, leaving holes that are almost immediately replaced by other electrons, coming from other atoms. That happens because the energy provided by the ambient temperature is enough to break the bonds between those electrons and the atoms to which they belong. And since these electrons are so free to move, as soon as we apply a difference of potential energy at the ends of the wire, the current starts flowing. All metals behave the same way, some more easily and some less, but in any case, the current in metals is always made of electrons which are negatively charged. But current can flow also in other kinds of conductors, not just metals. A saline solution, for example, is also a conductor. However, in a saline solution there are usually no free electrons going around. Instead, there are ions from the chemical reaction with the water. Some of these ions are charged negatively and some are charged positively. However, regardless of the charge, they are all able to move freely in the solution, so they both can participate to the making of the electrical current. In such a case, when a difference of potential energy is applied to the solution, for example through a couple of metal bars immersed into it, which we call electrodes, positive ions will move toward the negative electrode and negative ions will move toward the positive electrode simultaneously. So, summarizing, electrical current is made of electric charges, flowing in a conductor like the water in a river does. These charges have the ability of moving in a medium, like for example an electric wire or a solution. Like the water in a river, charges have to move from a higher level to a lower level of potential energy. For a river, the higher level of potential energy is the higher ground, and so the water flows from a higher ground to a lower ground, or in other words, from a mountain or a hill toward the valley below or to the sea or the ocean. Similarly, for an electric current, charges have to move from a higher ground of electrical potential energy to a lower ground. The problem with electrical current is that, as we have just seen, different kinds of charges can make it, depending on the conductor, and depending on the kind of charges. In other words, the definition of higher ground needs to be adjusted depending on the charges being positive or negative. Positive charges like to go from their kind of higher ground, which we call the positive electric potential level, to a lower ground, which is a lower positive electric potential level that we call negative to distinguish from the other one. And finally, we say that the negative charges like to go from their kind of higher ground, which is the negative electric potential level, to their kind of lower ground, which now we understand we can call the positive electrical potential level. This seems utterly complicated, and in fact it is. To be able to work with these concepts without making mistakes, we need to make some kind of assumption and introduce some sort of simplification. Let's say that whenever an electrical current is involved, we will always say that it is made up of positive charges, and that positive charges always go from positive to negative electric potential level. Now, it doesn't matter the medium being an electric wire where the current is made up of electrons, or the acid of a solution in a battery where the electrical current is made of ions, both positive and negative, that create two different currents flowing simultaneously in opposite directions. Let's now state our formal definition. We define the electrical current as the flow of positive electric charges in a conductor, whatever it is, going from the positive potential level to the negative. With this definition, we can address problems involving electrical currents always the same way, without worrying what is really happening behind the scenes. And this is a very important concept. All about electrical engineering is based on this definition of current, or at least most of it. Let's now go one step further. What are we going to do with this definition if we don't have a mean to measure the value of the current? If we cannot measure the value of the current, the concept of current itself is useless. Because if we want to build something that uses electrical current, we need a way to determine how much is too much, or how few is too few for the thing that we are building. So let's add some more to this discussion. We have said that the electric current is due to the flow of electric charges, and we have said that this works mano a mano with the concept of the water current in a river. For the case of the water, we already have a definition of the amount of current coming from mechanical physics. We say that the amount of current that flows in a section of the river equals the amount of water that flows in that section divided by the time the water takes to pass through. For the electrical current, we can reason similarly. We can assimilate the flow of charges to the flow of water, and then we can write the following formula. Electric current equals the quantity of charge passing through a section of the conductor divided by the observation time, or how time it takes for those charges to go through the section. From physics, we know that the electrical charge is measured in coulombs, abbreviated with capital C. The quantity of the electric charge of an electron is, besides the negative sign, Q equal 1.602 times 10 to the power of minus 19 coulombs. We define the unit to measure the current as ampere, usually called amp, and it is the amount of 1 coulomb of charge that moves through a section of the conductor in 1 second, or 1 amp equals 1 coulomb divided by 1 second. If the charges were electrons, for example, the number of charges needed to make 1 amp would be 1 amp equals 1 coulomb divided by 1 second, equals 1 coulomb divided by 1 second times charge of 1 electron divided by 1.602 times 10 to the power of minus 19 coulombs, which is equal to 6.24 times 10 to the power of 18 electrons, or 6,240 quadrillions electrons. There is one last thing that we need to talk about before ending the preliminary discussion on the electrical current. The electrical current we have talked about so far flows always in the same direction, and because of that, we call it direct current, abbreviated with DC, capital letters. But there is another form of current, the one that we extract, for example, from the outlet at home. That one is called alternate current, or AC. This is a current that flows for a while in one direction, then stops, then starts flowing in the opposite direction, then back again and again and again. Like the DC current, the AC current works going from the positive to the negative energy levels. The difference between the two is that the energy levels keep switching in the case of the AC. The positive becomes negative, then becomes positive again, and so forth, and so the current keeps changing its direction accordingly. Also, the AC does not change suddenly back and forth, but it does it a little bit at a time, following a shape called sine wave. All electrical energy distributed in our homes has this kind of shape. In the USA, in particular, the AC current changes direction 120 times per second, which means that in 1 second there are 60 full periods of the sine wave. We say that the frequency of the current is 60 Hz. In Europe, they use instead 50 Hz. Other parts of the world either use one or the other, but mostly the most globally used frequency is 50 Hz. And with that, we end this preliminary discussion on the current. Later on, we will address again these concepts and we will expand on them. Stay tuned. And in the meantime, happy experiments!